1K and 1 micro, right? Okay, 1K. So you go to calculator here. Okay, we work out RC, 1 kilo ohm times 1 micro, about 1 millisecond, right? About 1 millisecond. As one RC constant, about 1 millisecond. Look at the curve here. What happened to the signal at 1 millisecond? Is it 0.62? Can you see it or not? No, this is called RC constant, right? You are not only learn about RC constant, actually you can simulate the RC constant, right? So you can remember it, right? That's why overweight, when we're learning, we not learn about theory. When you can see, it's a way people learning, when you can see with your own eyes, right? Actually you are more convinced, you can remember. People better to remember the picture than remember the words. You realize that, right? This is how I learn. There's so many theory in my mind. Basically, my mind memorized based on picture, right? I picture it, and then I learn it, right? This RC concept is not easy for you to remember. Like some people, there's too many things, right? I forget. But in my mind already, I remember this kind of picture in my mind, so I can really remember it, right? So you can see that, actually you can simulate the RC constant, right? At 1 millisecond, really follow what you learn. 1 millisecond, actually the output rise up to 0.63, exactly like what we expect, right? That's why I say that you need how many RC constant to get a complete value? Almost 5. You look at almost 5, almost reach 100%, almost 1.
So what you do is you just use the amount of value that you can reach in probably 63.2% of the final value. Use as a reference, then you count how much time you will reach until the final value.
I based on one RC constant from the calculation R and C. So I know that at this 1 millisecond, basically my output will rise up to 0.62. And this basically RC constant. So in other words, that if you want to make your signal rise faster, what you do? Either reduce R or reduce C. Then you can get your RC constant, right? That a lot of times, sometimes books say about RC constant 1 RC, 2 RC, 3 RC, 4 RC. You cannot picture what people talking about, But for the graph, you can say, hey, actually 1 RC is like this, 0.62, the voltage right out. And after that become how much? 5 RC actually you almost reach the full level of output that required. Right? Correct? So this is the way you learn the RC constant. Interesting, right? Actually you can no matter the way I learn this during my the I was university, right? How I learn. I have a theory. After the theory I calculate. The next step what I do?
Simulation.
The third next step.
You try to experiment with it.
Yeah, use a breadboard. We pump input, receive from oscilloscope. So from that actually you cannot forget it. Like triple, double, the picture, that imagine of mine. Right, So now actually for me, when I talk about RC constant, that's why I can talk a lot of things because I experienced all these things, So I basically show you circuit how to simulate it, what an application look like, all lump together. Right? When you learn something, you must learn the theory and also application. How to apply this theory? So I tell you, in the inverter that I show all you, right? Especially the RC constant, right? How to make your signal rise faster? Sometimes you will go to high speed, right? You need to be rise faster, right? So how to make it rise faster? Of course, you need a bigger W. Or for a transistor so that it can reduce R on. Oh, you must know all these things, no? You increase W what for, no? It's to reduce R on, right? So it can RC constant smaller, so it will write faster. So all these things are interrelated, right? You must understand, you cannot say I just increase the size, but I'm not sure what the reason for that. Right? Increase the size actually reduce your R on. Why can you R on? Because the transistor basically is linear. Right? So this is how the thing works. You must know the whole thing. Right? You try to link one theory to the other theory. So you make your understanding very good, very fast.
So just to confirm, because just now you say like when we increase the width, so that makes the IDS larger, right? When it becomes larger, then we follow the equation.
So you increase the width.
We increase the width, then your IDS will increase.
You increase the width, your R on will reduce. R on. Okay. You look at the formula for the R on for the transistor. When you bias in a linear region, you increase your width, actually your R on will reduce. Okay, R on will make it faster. No?
Oh, it's the inverse. Okay. It's the inverse.
Okay. It's okay. So this is where we play around with the equation. So clear the RC constant is all, right? So your phi RC will reach there. Okay. Okay. And also last year we had designed one product, right? Actually for the product, right, when switching you cannot have the overshoot. So basically I use this theory to design it, so that I don't have the overshoot at the output. Based on this RC constant. Amazing, when you design something, you might have a theory. You are strong in fundamental will help you to progress.
But is there like a trade-off? Because if you want to lower down your overshoot, right, that means that your circuit will be more delayed. Correct?
Slower.
Oh.
Some system, right, because that product, right, is to bias, actually come with the voltage to bias the other block. It's a product, and if you have overshoot, you tend to make your biasing suddenly shoot up. So they rather have the slow, but don't have overshoot. This requirement. That's why in different applications it's a bit slow, okay, because it's DC biasing. But the key thing for them is you don't have the overshoot. And the datasheet say there's zero overshoot. I mean, you cannot guarantee that there's no overshoot at all at the output. Okay, so this is the key thing.
Interesting. I'm just wondering what will happen if, let's say, your application requires like no overshoot, but then you cannot exceed the time frame.
Got also, right? Got also. That's why we have this. If you, I can share this. Like it. That means that it's something. Last time we do. It's I still can recall back, That overshoot is very. That means that it's very slow to go up, right? After that, okay, sorry. It's like this. At this point, actually, we have something to make it very slow. Okay. Actually, we have something called one shot. One shot actually inject current to the output, making very fast at the beginning. Because overshoot happening at here, right? Correct. So we speed up the thing at this region, from here to here.
Okay.
When there's a one shot there, right? Inject current to the output to make a signal. Okay? Because after this, because overshoot at here, not at here, right? So after that, this guy coming down, it means that when go here, it very fast go up, okay? And here actually will come down.
Oh, okay.
You get no more no more the injection current there, right? So this is a way.
This one let's stop or
Oh, stop with it.
no. Now it's just now when I came in, it's halfway stop. So I don't know why. That's why I come back and check.
Oh,
Now it's running.
running okay.
The initial, I don't know how long it's recorded.
Oh,
But now it's running.
not running. Wait for half an hour.
Ah,
Complete. Not running.
is it?
Okay.
Already 10, just now I click it again. So it's still running.
You'll be here like another 30 minutes.
Huh?
You'll be here right until 5:30.
Ah, it's fine. Just look at this one.
Mm.
If you monitor this one. It's showing recording, right?
Ah, okay. If it is not recording, which button do I press?
Nothing. REC is record. So it's recording.
Okay. I think we cannot finish tomorrow another session. Under 5:30, yeah? Huh? Under 5:30.
Okay.
I'm so tired. Okay, under 5:30, yeah? Okay. So, you see a point, right, how to overcome that?
So when we inject the current, that means your signal will like speed up. But then at the same time, when the injected current falls back to zero, then the whole signal will actually fall down as well.
Yeah, correct. Correct. Inject current here. The sub-control signal
Okay.
to speed up things, but this is for a short while only.
Mm.
You will not overshoot here happen, right? No? So after that we slow down so it doesn't overshoot. So we play around with our constant also to solve that issue. Yeah. So now we go to the next one. I think the last one before we take a break. The last one. Okay. So you look at this one. It's a low pass filter, right? I think oh, you look at this really a bit scary, right? Actually not that tough, right? And this R, this C, actually called a low pass filter. Low pass filter basically it pass what? Low frequency signal and reject the high frequency signal. And look at here, right? Here, look at this formula. Remember, this is an impedance, this is a voltage divider. So you take the output here, you consider a voltage divider, right? So basically, impedance across cluster is 1 over SC, right? So basically, voltage divider, you take the total impedance R plus 1 over SC. So the bottom one is 1 over SC. So the time the SC become 1 plus SRC. So remember, this is a normal standard, right? For the pole, it's 1 plus SRC. 1 plus SRC. If you don't have this 1, it's called what? No? Why remember this? You have this 1 plus SRC equal 1 pole. S is equal to J omega. RC, S is J omega. J omega is a variable. What is your input frequency for filter? This one has J omega. Omega is your input frequency. No? That's why here define your S equal to J omega. What about RC? RC is a constant, which is defined by the R and C of your filter. It's a constant. That's why you have this equation. S is your input. RC is a constant, where the boundary is set by your RC value. Interesting, right? So in the equation, you must know where is your variable, what is constant, right? RC there is a value, is a RC constant, right? Remember this filter, RC is a small signal. The one just now we talk about RC constant is the last signal. So filter actually is a small signal. Okay? And this S is J omega. That's why this one will form a pole of minus. Later I explain more, but in the simulation. That means that you have your anyone familiar with body clock? Oh, familiar? Later I explain more. So remember this is one pole. What about this one? SCR only, SRC only. Why is that? You don't have 1 plus.
0.
No? You see at the bottom, right? Let's say I don't have
1
the-
over SRC.
Oh, 1 over SRC. Let's say I have a 1 over SRC. Or sometimes, no, let's say 1 over, sorry, 1 over S. 1 over S. Why is that?
Integrator.
Yes. This is we call pole at the origin. No 1 over S. Pole at the origin. So normally you have this let's say you have this S S plus 1 plus 1 plus SRC. No, it means that you have one pole at the origin and 1 normal pole. This is the meaning of that. You time together. The meaning of that. So if you look at the body plot, right, you see differently. So you look at the body plot for this, right? When you have original pole, you drop here, this is frequency, this the gain, so you drop by minus 20 dB per decade. Okay, and after that you need another pole here, you drop further, another slope. Sorry, we have to drop. Coming down. So at the end become minus 40 per decade, the slope here. Become minus 40. Okay, so this one basically is this is minus 20, this another minus 20 become minus 40 here, the slope here become minus 40. Okay, that means actually you have 1 origin pole plus 1 normal pole. This normally I call it normal pole. And this 1 over S normally we call as a you can call it as an integrator. It's an integrator.
I'm still cannot follow.
Oh.
There are 2 poles. The first one is 1 over SRC.
1 plus LRC is a normal RC, no?
So from the graph just now, it is shown at the first one, negative 20.
This original pole, origin pole. 1 over S. By this guy. Actually, there's a denominator.
Oh, doesn't come in there. Okay, so what I'm trying to say is, when you have 1 over S, right, that means that you have a pole right at the origin. So at that point, the signal when you approach the right side, it will immediately drop by 20 decibel per decade.
Yeah.
But then there's also another one which is called 1 plus SRC. So that means that there's also another pole, a normal pole somewhere on the right side.
Yeah.
So once you reach that point, the signal will drop by another minus 40.
Minus 20.
Oh, sorry, minus 20.
In total become minus 40.
Minus 40.
Understand?
So you measure the slope caused by the 1 plus SRC. The slope is actually minus 40.
Yes. They add together become minus 40. Each one contribute minus 20. Four at the origin minus 40, and this one contribute another minus 40. Minus 20. So total become minus 40. Understand, right? So become minus 40. Okay. So I want to teach you a simple simulation of that to understand further about all these things. Example I mentioned to you. One pole actually contribute how much of phase shift maximum?
1 pole contribute how much of the phase shift?
90.
190. So I'll show you the simulation of that. Okay. So how to do a simulation of that? This RC filter, right? You change one become none here. Okay, we put AC1 here. Put AC1 here. Okay, now we run the AC analysis. Anyone? I think everyone have run the AC solution before, right? So come here. So we go to AC analysis. We start on the time step is type of step we use decay. Decay means that what?
The log scale.
It means 1K, 10K, it always times 10.
Oh.
1K, 10K, 100K, 1 mega. Oh, this is the meaning of that. So number of 1 per decay, I always put 100. I'm more accurate. I'll start from maybe 1 to maybe 100 mg, right? So I will show you more detail about this RT filter. As you know, RT filter is a pass the AC. You look at more things, you can learn more things here. Look at the graph here. Yeah, as mentioned to you, this is called decay. 1 Hz, 10 Hz, 100 Hz, 1K away times 10. Alright? So look at the waveform here. Right? Look at the waveform here. Now, how we define the bandwidth of your how you define the bandwidth of the signal, right? It's always minus
3
minus
dB.
3 dB. Look at here. Yeah, that. Okay. It's about 160 hertz, right? So how we can get this value?
Through the when you cross it, I mean on the x-axis.
Yeah. So from calculation, how to get it? It's OA F equal to 1 over 2 pi RC. So can I try to calculate this value? Your R is 1K and C also 1 micro. Try to calculate that. How much?
Your calculator.
You use my phone calculator.
My phone is done.
2 pi plus.
How much is the RNC?
R is 1K.
1K,
C is 1 micro.
About 159 hertz.
159 hertz.
159.154. Sorry, 155.
Okay, it matches the calculation, right?
Very close lah, very close.
Very close. And this is what we call as a cutoff frequency, right? It means that any input frequency below this actually will pass through, right? And what? But actually, the RC filter, right? Actually represent the pole of your system, right? So you must know, and these dot lines represent the phase shift. Actually, what is the phase shift to you in time domain?
Different directions.
Oscillation.
No.
Because output.
Actually, when before we talk about oscillation, right, all this stuff, right, no. Actually, in the body plot, you have the phase shift, right? This a gain plot and this a phase plot. Actually, in this plot, right, when we translate the time domain, we In time domain, actually, what is that parameter?
In time domain.
Called. We call propagation delay. Phase shift is equal to, it tells you the information about the delay between your input signal and output signal.
Oh, okay.
Okay? It tells you that. You know? So how much the phase shift at certain frequency, right, at your input frequency, will tell you how much the delay between your input and output. Right? Let's say your signal in this way. Right? Your signal is like this. This is your input, right? And this is your output. There's some delay. Right? And this delay actually it coming, if you divide input frequency, look, input frequency delay actually coming from a phase shift. The phase shift at what frequency? How many degree? Let's say I click here. This how many degree, right? This is 89. This 34 degree. Actually, what I do is it's not made like that, right? I look at this okay. Normally I put you know about what's persamaan serentak, or we call that simultaneous equation. The video what I do. Let's say I put it this way. Let's say I have 1 megahertz. 1 megahertz, what is the phase shift? Actually the full cycle of the clock is 360, right? Up to 360. Right. Now I want to know the so 1 megahertz is your time now. Now I look at my, let's say I want to find at what frequency. Let's say I want to find at 100 kilohertz. Okay. Signal that coming in, right? What's the phase shift? Let's say it's 30 degree, right? So I put here 30 degree. And I put T here. This T actually define my delay between my input and output signal. You understand?
Where did 1 mega come from?
Let's say my signal here is a 1 megahertz. 1 megahertz signal. That's it. 1 megahertz signal. So I want to know the delay here between my, let's say I have an inverter, right? I have whatever thing. I want to know the delay between here and here. This percent here. So basically I know, okay, 1 megahertz is equal to my 360 degree phase shift, right? Here to here is 180, here to here is 180, so total is 360 for 1 megahertz, right? So yeah, look at let's say my input frequency is how much? Let's say I saw it 30 degree, right? Then from 30 degree, I back calculate, I can find what is my delay between my input and output signal, right? So I try out you that the phase shift is important parameter, not only for stability check, but also for you to know what is your delay between your input and output. This is important information. It means that if your phase shift is more, basically you have more delay, right? That's why you never use any input signal larger than your bandwidth. Okay, look at here, right? When you reach your bandwidth frequency, what is the phase shift?
40 something.
Always same one. It's a standard. Always 45.
45 degree.
When you have one pole, when you reach your cutoff frequency, the phase shift is 45 degrees. Standard. You never change. Okay? 45 degrees actually the delay is a lot already. That's why we never use any input frequency more than your cutoff frequency. The other reason because there's a lot of delay. It's already 45, half of the delay already done. One pole, how much the delay maximum? 90 degrees. You see or not?